Hello everyone. Today we're going to start on 2.2 matrix methods. So the general idea here is to try to use this thing called matrix to try to solve a system of equation. So before we get started, let's talk about what is a matrix first. A matrix, as a matter of fact, a lot of you already know what it is, but let's try to define what it is. A matrix is basically a rectangular array of numbers. Well, technically speaking, it doesn't have to be numbers, but for us, it will be a numbers. So example of a matrix would be something like this. 0, 3, -1, radical 2, 2, 1. So that would be a matrix. This is also considered to be a matrix. As a matter of fact, vector that we know are also considered to be matrix also, such as these two. However, we write it as a matrix. We usually don't use comma to separate the numbers inside. So these are all examples of matrices. In a matrix, the horizontal array of numbers is usually referred to as a row. Or sometimes referred to as a row vector, because it kind of look like a vector. So therefore, this last one right here, that will be an example of that. There will be a row vector, and this one will have 1 row, 2 row, 3 rows. The vertical arrays of numbers is called a column, which is sometimes called a column vector. So example of that would be like this one right here, where you go vertical. And this one, if you look at the first example, then you see that this has 2 columns. And then this one also have 2 columns. But the first one have 3 rows, and the second matrix have 2 rows. And whenever we describe a matrix, we usually also describe what we call the dimensions. So the dimension of a matrix is often referred to by the number of rows by the number of columns. So rows by columns, that's how we generate a matrix. So therefore, in this case, if you look at this example right here, so this one is a 3 by 2 matrix. And you can see that it has 3 rows. Let's see if we can highlight them. Oh, actually, maybe I can use this. Let's see if that works. I don't know. Maybe not. Okay, maybe I'll do this instead. So this is, excuse me, row number 1. This is row number 2. And then this is row number 3. And then you can also define columns. So that would be columns number 1. And this is column number 2. Now, one thing that's interesting to note is the following. Well, each of the numbers inside a matrix is often referred to as an entry. So notice that each entry is actually must be on a specific row and a specific column. That's how you identify where this number is within the matrix. So keep that in mind. It becomes important later on. Whenever we define a function, in general, this is how we define a function. define a matrix. So we usually use a capital letter in general. An n by m matrix will be in the form of. So we usually use a capital letter to name a matrix. So that's, once again, it's not like a rule, but it's by convention. So therefore, you'll see that I usually represent or name a matrix using a capital letter. Just like I would name a point, would be using capital letter, but then a vector usually use lowercase letter. So for matrix, we usually use a capital letter. So let's say I'm going to define this matrix A. So I'm going to name it with capital A. And this is how we're going to identify the entries inside. So to show association, we will use the same letter but lowercase letter to indicate entries inside. So it's kind of similar to vectors where we use the same letter as the name. But the difference is that vector would have to be a lowercase letter with arrows on top. So here I'm going to go and call this A11. So notice that the 11 is not 11, but actually is 2 separate subscripts. Okay, and it's not the first time you see this. You saw this in 2.1 already. A11, A12, and then this pattern continue on to A1M because they have M columns in this matrix. And then our second row will be A21, A22, all the way to A2M. And then this thing continue on to AN1, AN2, and then all the way to ANM. And in this case, where A sub ij is the entry at the ith row, so the first subscript indicate what row is on, and jth columns. So the second subscript indicate what column is on. So therefore, if I say A23, then you will know it's the second row, third column entry. All right. So pretty straightforward to try to outline a matrix. And it shouldn't come as a surprise that an n by m matrix will have n times m that many elements in it. In a sense, that's kind of like the area of a matrix. It's the number of elements within the matrix. Now, last thing I want to talk about before we move on to something else is that there is this very special kind of matrix called a square matrix. A square matrix is a matrix with the same number of row as column. So essentially, if you think about it, a matrix is a rectangular array of numbers, then a square matrix would be like a square array of number, which basically meaning something like this. A very simple example. So this would be a 3 by 3 square matrix because the number of rows and columns are the same. Or you can have something like this, which is a 2 by 2 matrix or 2 by 2 square matrix. Now, remember, what we're going to try to do is try to figure out how to use matrix as a method to help us solve the system of equation. And here's the interesting thing. Using matrix to solve a system of equation does have its advantages. But the most important part that we want to use that is rather for bookkeeping purposes. So meaning that one of the major reasons why we use matrices to solve a system of equation is simply because mathematicians don't want to write. They don't like to write a lot of stuff down. And they realize that when they're solving a system of equation, they're rewriting a lot of the same thing over and over again. And so they decided, well, let's develop a method that would just keep track of all the numbers and forget about everything else. we just assume all the other things are just stay in place. And then we just simply keep track of all the numbers. And then once we're done with all the numbers, then we just kind of make it back into the problem. So the way it worked is the following. So in order to actually do that, I do have to define something first. Because without it, I won't be able to actually transform a system of equation into what we call matrix form. So next thing I want to talk to you about is this, is how to multiply. Multiplication between a matrix and a vector. So, show you how that works. So to multiply a matrix by a vector, best way to do is to show you an example, and then I can illustrate the process. So let's say I try to multiply this matrix with this vector. So important to pay attention is the following. Whenever you talk about multiplication using matrices, you have to pay attention to the dimension involved, because there's certain requirement in order for multiplication to be defined as valid operation. So this is how it works. So if you look at this problem right here, notice that I have 2 by 2 matrix multiplied by 2 by 1 matrix, or a column vector. Important to realize is the following. In order for a multiplication to be valid, these two numbers must be the same in order for the multiplication to be valid. So meaning, if these two numbers are not the same, you actually cannot, to be valid. Therefore, it implies that if these two numbers are not the same, your multiplication is actually invalid, and therefore it cannot be done. Okay, so very important to understand that. And then more interestingly is the following. These two numbers form the dimension of the product. So in this case, if I do this multiplication correctly, the output will be a 2 by 1 matrix. Now, how do you actually multiply a matrix and a vector together? The way to do that is to use something that we have already learned. So whenever we're multiplying a matrix with a vector, we're basically doing dot products between each row of the matrix with the vector. So that's how you actually perform multiplication. So therefore, what does that mean? So in this case, if I multiply this together, what I have would be the dot product between 1, 2, which is the first row, dot product with the vector 5, 6. That result in the first row. Then we take 3, 4, dot product 5, 6, and that result in the second row. And now what I have here would be a 2 by 1 matrix. So you basically take the first row and dot product the vector, and you put that as the first row of your result. And then you dot product the second row of the matrix with the vector, and that becomes the second row of the result. So now all you have to do is just simply do dot product. So I assume you can do that. So if you simply do the dot product, you realize the first number is 17. The bottom number would be 39, if I'm not mistaken. And that becomes the answer. Now, I know it's kind of weird to do a multiplication this way, but that's how we define the multiplication between a matrix and a vector. Now, I'll show you another example. How about we do this one? So before you actually set out into doing your multiplication and stuff, what you really have to do is to first look at the dimension. So what is the dimension of this thing right here? Well, that would be a 3 by 2 matrix. And this right here is a 2 by 1 vector. Notice that these two numbers in the middle are the same, therefore allow me to multiply them together. And the output should be a 3 by 1 matrix. So what would this 3 by 1 matrix look like? Very simple. Actually, you know what? Let's write this out. So there would be 1, 0, dot product, 5, 6. 2, negative 1, dot product, 5, 6. 3, comma 2, dot product, 5, 6. Now take a minute to do your dot product and see if you can come up with the correct answers. So it shouldn't be too hard. The first one should be 5. The second one should be 4. And then the last one, 15 plus 12, is 27. So note that we have a 3 by 1 matrix. Now, the interesting thing about this process is that I can actually use it to represent a two-way expression with this. One way to do that is to simply just multiply a matrix with numbers with a vector that is a variable. Like in this case, if I do 1, 0, and 2, negative 3 multiplied by xy, that will become the dot product of 1, 0 with xy, and then 2, negative 3 dot product with xy. And notice what it come out to be would just be this, x 2x minus 3y. Notice that the matrix simply become kind of the coefficient in front of the x and the y, and which is how we want it to work. Now, with that being done, I can now show you how to rewrite a matrix, the system equation into matrix form. And of course, we're talking about a linear system. So we write a linear system, or a system of linear equations, into what we call matrix form. So show you how it's done. Let's say we're given, so in here I'm going to basically, for example, let's say we're given a system of linear equations. And let's say in this system we have n equations with m variables. So like 2 equations with 3 variables, or 7 equations with 5 variables. So n represent the number of equations involved, and m represent the number of variables involved. So how would this system look like? So the system will look something like this. It will have a coefficient a1, 1, and then the variable x1 plus a1, 2 with the variable x2 plus dot 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 plus a1m with the variable xm. So in this scenario right here, we can think of the m variables as x1, x2 to xm. So maybe I will put that down here. So you know what? Maybe I'll do this. Maybe I just oh, nope. That's not what I want. Okay. Let's move it down. And then I can just write it in. Okay, so I'm going to let x1, x2, dot 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 to xm be the m be the variables. So therefore now I can write out my equation, and that's equal to some constant on the other side, which I'm going to call it B1. And I'm going to write out my second equation. My second equation will be A21x1 plus A22x2 plus dot 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 plus A2mxm, and that's equal to B2. That's my second equation. And let's say this pattern continue on. To the last equation. And the last equation would be an1x1 plus an2x2 plus dot 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 plus anm xm equal to bn. Now, if you have a little deja vu, you should, because notice how I named the coefficient in all this equation is actually kind of the same way that I'm naming them in a regular matrix form. And that's precisely how we want to do it. So let's say this is my linear system. So this is a system of linear equation. What I want to do is simply transform it into a matrix equation that looks something like this. Notice that's looking a lot simpler. So this is what we call the matrix form. So in this matrix form, I want to show you what these three things are. So in the matrix form, there are basically three matrices that we want to use to transform this system of equation into. First is the matrix A. A would be the matrix A11, A12 to A1M, A21, A22 to A2M, dot 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 to AN1, AN2, ANM. This is called the coefficient matrix. Why is it called a coefficient matrix? Because simply collect all the coefficients together and you don't even change the way the coefficient look. Ooh, okay. What happened here? I don't know what happened here. Why is it all messed up? Let me fix this. Okay, that's good. AN1, AN2, dot dot dot, ANM. Okay, there you go. I don't know why that got messed up. But it's called a coefficient matrix because it literally just basically take all the coefficient and just put them together into a matrix. And that's it. What is vector x? Vector x is simply the variable that we have, which in this case will be x1, x2, dot 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 to xm. Now notice that these are just basically what we refer to as the variable vector. And in this case it has to be a column vector. Okay, and I'll explain to you why that is the case. And finally, you have the vector b. So vector b is just b1, b2, dot 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 to bn. And this vector b doesn't have a special name. It's usually referred to as the right side matrix or the right side vector, because usually it's on the right side. And it also has to be a column vector. Now, why does it have to be a column vector? Because of the dimension involved. If you look at matrix A, notice that matrix A, it has to be an n by m matrix. In order for it to be able to multiply to vector x so that the multiplication can be carried out, vector x must be an m by 1 vector and therefore become a column vector because I have only one column. And so now when I multiply this with this, the m would be equal and therefore allow me to multiply them together. And the output of this multiplication would take on the n and the 1 because those are two outside numbers. So therefore, it has to be an n by 1 right side vector, which in this case would also be a column vector. Now, it might sound complicated, but it's actually very straightforward to do. So show you how it's done. Give you some example to try it out. And that actually might be the last thing that we're going to talk about today in today's video. So example, let's say rewrite the following system into matrix form. So A, how about this system? So pretty simple. So remember, when you write it into a system, you want into matrix form, you want it to be this. So therefore, basically just means you have a matrix A, you have a vector that identify the variable, and then you have the right side vector, which is what the equation equal to. So what should it be in matrix form? Actually pretty simple. This is what you do. You just basically write down the 4 number that you see in this case. Then you have a 2 by 2 matrix. Now why is it a 2 by 2 matrix? Remember the following. When you look at your coefficient matrix, the number of row that determined by the number of equations in the system, and the number of columns that's indicated by the number of variables involved. Now what I put in here, which is the variable vectors, in this case the two variables x and y, and you do have to put them vertically, and then this is 1 and 2. Now sometimes it can be a little tricky when you do this, so I want to show you this example to illustrate. What if you have these two systems? What should it be when I write it into matrix form? So feel free to pause the video and give it a try first before I show you what the answer would be, okay? Now hopefully some of you notice something fishy about this one. Notice that if you look at this system right here, you should see that you have x, y, and z. So there are technically 3 variables involved. Now however, both of the equations only involve 2 variables. So the tricky part is to understand that even though each equation only involves 2 variables, but the entire system actually requires us to have 3 variables. And so you have to learn to properly identify what the system looks like. So first thing you probably want to do is to actually rewrite the system into this first. It's 2x plus, I'm going to put down y equal to 4. And then we'll put down negative y plus z equal to 2. Notice how I space them out because I want to fill in some numbers here. Plus 1y plus 0z. When there's no z involved in the first equation, it simply indicates that the 0 coordinate in front of the z. Therefore, 0 times z, go away. And notice the second equation doesn't have x, so same exact ideas. That will mean that 0x, and instead of minus 1, we'll say plus negative 1y. And then plus 1z. So now I fill in all the missing things, and this is not a difficult process, and it's not even the first time you see this. We did that when we tried to rewrite something in parametric form, which I told you that you have to line things up and fill in the missing numbers so that you can see how it works. So now I can rewrite this into a matrix form. So notice that there are 2 equations but 3 variables. Therefore, we have a 2 by 3 matrix here. The matrix, the coefficient matrix will be 2, 1, 0, 0, negative 1, 1. It will multiply by x, y, z, and come out to be equal to 4, 2. So if you look at the dimension, you should see that it works out. It's a 2 by 3 matrix. This vector right here, XYZ, is a 3 by 1 vector. So notice the 2 3's in the middle that allow me to multiply them together. And the two outside numbers are 2 by 1. Therefore, that's why the right side vector is a 2 by 1 vector. Now, once we can rewrite it into a matrix form, we can then learn how to solve a system using this process. And that will be what we go talk about in tomorrow's videos. All right, talk to you guys later. Bye-bye.